What's that?
I just say that's how it goes.
Yeah, it does. In fact, most days it seems like. Oh man, I blew it. But I think I can correct it. Okay, I think this is the slide we're on. And it hasn't come up yet. But let me make a couple of announcements. Well, let me first mark the roll. It's going to be tough. So many of you here. Boozer's not here yet. Justin's not here yet. Nathan's not here yet. Tyler's, see, I did hear from Nathan yesterday, so I'll go and mark him. Tyler, not here yet. Okay. Elijah's not here yet. Terrell's not here yet. Jeremy's not here yet. David, right? Okay. Okay. Increase the class size by 50%. Way to go. Diamond's not here yet. Nicole's not here yet. Taiwan's not here yet. Kenesha's not here yet. Anhil is here. Brianna's not here yet, but Cheston's here. Okay. 3 back road. They're all filled. Okay, we'll work our way around. Okay. Oh, Tyrell decided to show up today. Okay. Amazing. Okay. All right. I shouldn't have called roll online. I don't usually do that. I meant to call roll before I turn on the system. But I got it backwards. There are a couple of announcements I want to make sure that everybody hears. That's why I wanted this on before I made the announcement. Today and tomorrow, Lawson State Community College is having college transfer fair days today and tomorrow. This morning is starting now, 9:30, goes to 11:30 on the Birmingham campus. So I doubt if you'll have time to make it. If you leave here at 11:10, when this class gets out, you barely make it there. That's the academic building. That's Building B. I think it's that long hallway back there in the back. However, they will be here tomorrow on this campus, 9:30 to 11:30. Okay? So as long as you don't have a class then, okay, Harrison, is that right? Okay. And is it Kenesha?
Brittany.
Oh, Brittany. Wait.
Brittany. Nicole.
Okay. There you go. Okay. Rutledge. Okay, that's what you were saying. My hearing is so bad. All right. Just making the announcement about Lawson State Community College college transfer day, fair days are today and tomorrow, 9:30 to 11:30, both days. Today it's on the Birmingham campus, 9:30 to 11:30. Starting now, and if you stay through the end of class at 11:10, you'll barely be able to get there. But they'll be on this campus, Bessemer campus, tomorrow, 9:30 to 11:30. All right. And let's see. Diamond? Okay. I have a real good memory. It's just short. Okay. So tomorrow, 9:30 to 11:30 here, and they'll be in the faculty, they call it the faculty campus cafeteria. You know where the cafeteria is? You don't know where it is. Okay. Let me sort of point it out on the map. Okay. Now, this only shows second floor. It's down on the first floor. To get there from here, go out the door here, and then go down this long hallway and go to that second stairwell, not the first stairwell, the second stairwell. You then wander around there, and you'll see the faculty staff dining room right there. They list it as second floor, but it's actually first floor here. The cafeteria is behind it here. It is first floor. It's on the same level. I don't know why they have that one, but it's right there. So go out here. Now, if you're coming in a different way, if you park on the back side of the building, which is where the student services entrance is, there, I'm sorry, that's this side, the easiest one, there's the main entrance is right here, There's two other doors here. That would be the closest, but the main one's not bad either. It's right next to the cafeteria. And the signs for the cafeteria are all around. Faculty, it's called Faculty Staff Dining Room is what it's called. And they call it Faculty Campus Cafeteria. So whatever. The faculty hardly ever use it. Okay. So anyway. Now, institutions that are scheduled to attend, both today on Birmingham campus and tomorrow here, I mean, there's a list and a half of them here. AUM, Mississippi State, Oakwood, University of Alabama, Montevallo, Alabama State, Auburn University School of Forestry and Wildlife Sciences, Alabama A&M, West Georgia, Auburn, Jacksonville State, Stillman College, University of Alabama is coming twice, I guess. Okay. UAB, UAH, West Alabama, Troy University, South Alabama, University of Alabama College of Continuing Studies, Athens State, UAB School of Health Professions, University of North Alabama, Samford University, Fisk University, Mississippi College, Concordia College, Tennessee State, William Carey University, Avita Institute, Birmingham. I'm not sure what that one is. Okay. Armstrong State, Faulkner University, Southeastern Bible College, Talladega College, Georgia Southwestern State University, and Berea College. Okay. The only reason I went through them all for people not here, hopefully you could hear that, and that would be 9:30 to 11:30 here on this campus tomorrow. If you're here before it's over with on the Birmingham campus. All right, one other announcement. This won't be quite as long, but it's aimed at you guys in particular. If you will be here still at Lawson State next fall, or any of you already going to be through, you'll be here? You'll be through. Okay, so you can ignore this one. Okay. But if you are going to be here next fall, the math team, okay, the name of the math team are the prime examples, okay, for prime numbers and prime people, okay. Miss Nyla Geraci is a math instructor. She's trying to build a strong math team, so please, she's asking us if we have a student in Math 100, 112, 113, or 125, okay, who will be at Lawson State fall of 2018, and it says, and they need calculus. That's the main thing they're looking for. Send them to Friday to C100 on the Birmingham West Campus. The C building is called the Science Building. C100 is a classroom there. And we're going to have our meetings at 12 noon every Friday on the Birmingham West Campus in C100. So if you can go, if you can't go this time but can other times, please contact her. I have her email address. It's ngeraci. If you need a spelling, come see me after class. I have her office phone number, 929-2009, and her office is in the C building also. It's just upstairs in room C210. So please, if you can, it's a lot of fun. And if you want to, have some practice, that's what she's planning to have on Friday. But if Fridays at noon is inconvenient for you, check with me and we'll work out a time on this campus, okay? If Birmingham's inconvenient, I can work out times here. You can look and see my office hours. Anytime during office hours, I'll be glad to have. They're really fun times. The competitions are in the fall, but if we wait till fall, we don't have any practice time. So that's why we're trying to get started now. So let her know if you're interested. Let me know if you want to have practice rounds out here. We can do it. They send out questions they've used on previous ones, and we can get used to what it's like and do that type of thing. All right, any questions? Sorry, that took longer than I intended. Any questions on anything so far? Okay, we just got started. Last time we did 1.1 and got started on 1.2. Didn't get very far along in 1.2. This is where we left off. Okay? Now, here's the function we're dealing with. F of x is equal to x cubed minus 1 over x minus 1. We've already, I told you last time analytically how we could do this, and we did it. But let's do it numerically. That's what they're big on right now. So let's do it. If you write down that that function, f of x equal x cubed minus 1 over x minus 1, okay? And then let's start plugging in some values. We know that it's not defined where? Okay, I'm sorry, not defined. It's indeterminate where? X equal 1. So what we're going to do is start with values close to 1, but not 1. Okay? So that, let me write it down here so you'll see it. Okay? Whoa, let me get my pen. Yuck. All right, this is Taiwan. By the way, we were required this week to enter the no-show report. That's any students who were registered for the class but haven't shown up yet. This class, 100% of the students who are registered showed up, and in one of the first 2 days we met, now the third day we've met, my only class that every one of you had been here. Way to go. Of course, my best class ever, right? Okay, so let me fix this. All right, here's your function, f of x equal x cubed minus 1 over x minus 1. Same one we were dealing with last time. So if you plug in 0.75, cube it, subtract 1 from it. I would do an equal sign there, then divide by, I can do this one in my head, negative 0.25. See what you get. Anyone got it? You get anywhere close to this? Now, another way you can enter that, I hope you know your calculators well, you could open this with a parentheses. Parentheses, 0.75 cubed minus 1, close parentheses, divided by negative 0.25. Get this? Okay. How about 0.9? A lot of busy work here, but you'll notice here, increase to 2.710, right? 0.99. We're getting closer and closer to 1. We can't go to 1. If you try to put a 1 in here, your calculator won't do it. Error, error, error. Okay, right? So, get close as you can. 0.99, you got 2.970. 0.999, 2.997, blah, 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 blah. Okay? Looks like it's heading somewhere to 3. Now, we did this last time. Did we get 3 when we did it analytically? Do you remember what we did? Great note taking, right? Okay. I think we did plug that in, didn't we? Remember how we did it analytically? It was a long time ago, at least 2 days. Yes, sir. Okay. Let me pause this just a moment. All right. What we did before, remember? We factored this. X minus 1 times, remember how that factored? Anyone? X squared plus X plus 1, wasn't it? Huh? Yeah, I believe it was. Okay. Divided by X minus 1. Then the X minus 1s go out, and 1 squared is 1 plus 1 plus 1 is 3. And sure enough, that's what it gets through this way. So if you plug in f of 3 up here, that does give you an exact answer because you got rid of your X minus 1. But in the original problem, you don't get rid of it. It's still there, so you have a hole in the graph there. And that's going toward 3. Okay? Now, that's from the left. As f of x approaches, as x approaches 1 from the right, in other words, get greater than 1, 1.25, and Justin's here. All By the way, I don't know if all of you heard this or not. I did get the first paper in for the term from this class. I said best class ever, right? Of course, okay? So research papers can come in anytime, sooner, better than later, okay? So here we have another one. Let's plug in 1.25 here to this one, okay? And Brianna, is that right? Okay. I have a really good memory. It's just short. Okay. So. All right. You plug in 1.25 cubit. Well, if you want to open parentheses first, you can. Cubit, subtract 1, either close parentheses or hit equal sign, and then divide that by 0.25. I can do that in my head. And you'll get a bigger number. Still positive, by the way. Then do a 1.1 in here, 1.1 cubed minus 1 divided by 0.1, and you get this one. 1.01 cubed minus 1 will be a pretty small number. Divide that by 0.01, you get this one. And 1.001, getting closer and closer to 1. You can't plug a 1 in. Getting closer and closer, you're getting closer and closer to 3 from the right-hand side. So you're getting closer to 3 from the left, closer to 3 from the right. Obviously, the limit here, the value is not indeterminate, okay? But the limit of it coming from the left or the right is 3. That's how it looks numerically. Does that make sense? That's what limits are about. You can't plug in a 1, okay? You just can't do it. But you can take the limit as it gets closer and closer. Okay. Now, if this was one of those undefines, the closer you get to 1, it's blowing up. I mean, it's either going very large positively, like 3 million, or very large negative 2.7 million. Yeah, it's not, have a limit anywhere. It's getting extraordinarily large in one or both directions. Okay. Okay. Now, if you did the graph of this one, and I think I said to you before, remember when we did it, that came out a parabola, and sure enough, this is what it looks like. Really easy points to plot on this. Not many of them are, but this one's really easy. Plug in a 0. Alpha 0, you get minus 1 over minus 1, that's plus 1. There's 1 point, okay? Because it's a parabola, you know there's another point over here that matches it, but you don't know exactly where that would be. Jeremy's here. Okay. And, but if you were, well, actually what you do is divide like we did before and make this x squared plus x plus 1. Plot that as your parabola, but what you have to do is leave a hole here at x equal 1. Because x can't equal 1. You still can't divide by 0, but it's not a undefined form, it's an indeterminate form. So sure enough, this shows you as you approach it from the left or from the right, you're approaching 3. And just like the numbers we saw, these numbers from the left are less than 3, but approaching 3. These are greater than 3, but approaching 3. Okay? As x approaches 1 from the left to right, the alpha of x is approaching 3 from left to right. Make sense? So we can now say, and here's how we write it. The limit of that function, alpha of x, where it is, right over there, as x approaches 1. You can't plug it in, but the limit is 3. The value of the function is, as you get closer and closer, it's getting closer and closer to 3. So it has 3 as its limit. Okay? That's numerically. Kind of a pain in the neck, all those calculations, but it works for you. Okay? This discussion leads to an informal definition of a limit. Hopefully later today we'll get to the formal definition, which is just as big a pain, but it is there. But if f of x becomes arbitrarily close to a single number L, as the function gets close to some number L, as x approaches c from either side, the function's getting closer this way as x is approaching this way, then we say the limit of that function as x approaches c, even though you can't put x equals c in there, is that value L. Okay? So that's how we do it. The limit as x approaches c of f of x is equal to L. Okay? Now, in our problem, this was x approaching 1, f of x was approaching 3. Okay? Now, does that mean you can't ever plug in the c for x? No, you can. And if you plug it in, you get that, you've done it. Okay? Piece of cake. It's just plugging it in and evaluating. So quite often that's the case. However, the questionable cases are those where you can't plug in x equals c, and then you have to see what the limit is. Okay? So here's example 1, top of page 53. Evaluate the function f of x is x over the square root of x plus 1 minus 1 at several values of x near 0, and use the results to estimate the limit. That looks like a lot of fun, doesn't it? Okay? Well, that's first. First thing you do, I'm going to cut through some of the detail here. First thing you do, plug it in, see if you can. Well, what does the numerator become if you put x equals 0? 0, okay? Now, if the denominator is anything other than 0, you know what the limit is, 0. But if the denominator is 0, then that's what we call an indeterminate form. So let's see what the denominator is. So x approaches 0. What is in the radical? 1. Square root of 1 is 1. Minus 1 is 0. Okay. So, what they want you to do is plug in a bunch of values close to 0. Okay? Now, that's a nice little exercise, and when you're at home and have plenty of time, let's do it. Let me show you, and I'm jumping way ahead here, but to me, analytically, makes so much more sense. Here's a trick. And as my calculus professor in college said, we actually finished, I was fortunate enough to have one of the best professors in the department, and I had all 5 terms, this is back when we were on quarter system, all 5 courses of calculus under that one guy, and he was good. And we actually finished that 5th round a little bit early, had maybe a week or 2 left, and we were in class 5 days a week, 50 minutes a day, 10 to 10:50 every day, okay, Monday through Friday. And as he said, well, we finished this, let me get you ready for differential equations, because all of us are going to that next. And he started telling us some things about this. Helped big time. I mean, I breezed through differential equations because he reviewed some stuff with us, or presented stuff to us in a week or so. He said, but with differential equations, it's a little like this. You try tricks to see if you can get them to work. If they work, you call them a method, okay? Well, I'm going to show you a trick here that you will then use as a method. Now, this works when you have radicals, either in the numerator or the denominator, okay? Back when you first took up radicals, you remember this technique they called rationalizing the denominator? Okay, that's what we're going to be doing. Except if this had been in the numerator, we do a rationalize the numerator, okay? So we're doing the same thing. Now, the main purpose for rationalizing the denominator is sort of passé. You really don't need to do it anymore. You got calculators, you got computers. You can calculate these things just as they are. But back in the day, y'all don't remember this, Back in the day, before calculators, before computers, you had to do these things by hand. And if you had an irrational number in the denominator, you had to divide some irrational number that went on forever, and you just had to round it off somewhere into something else. And then you had to move the decimal here, you had to move the decimal here. You had great big numbers you were dividing into great big numbers. It was a real pain in the neck and other body parts, you know, but it was pretty miserable, okay? So if you rationalized the denominator and made it a rational number, 3, 7, 2.5, you only had 2 digits, 3 digits, 1 digit to do into, and you could have a bunch of digits in the numerator, but you could almost do those in your head sometimes, okay? So that's why they originally rationalized the denominators. Now, you got calculators, you can plug them in, they do all the work for you, right? But in limits, you still want to rationalize, either numerator or denominator. Do you remember how you did this? Rationalize the denominator like this. Okay, you multiply, you said by what's in the radical?
Yeah.
Not quite. Okay. Good guess. If that would have been your denominator, then you multiply by what's in the radical, and you do that numerator and denominator. You move the radical upstairs, and this becomes rational. Okay? But you have something else in here. So there was another technique we used. You did that if that's all you had, but since you had some other term here, what did you do? Anyone remember? You sure right? No, I'm sorry.
Tyler.
Say that one more. Oh, Tyler. Okay, Tyler. Sorry, I was just looking at you. Okay, Tyler. Okay. All right. Does anyone remember what a conjugate is? If you had A plus B, what's the conjugate of that? A minus B, exactly. So what we do is multiply by the conjugate, okay? And the conjugate of that denominator would be what? The square root of x plus 1. Say again? Plus 1. That's the conjugate of that. You change the difference to a sum, okay, and multiply. But if you multiply the denominator by that, guess what you got to do? Multiply the numerator by that as well. X plus 1 plus 1. Okay, now be sure you end the radical at the right place. Okay, now, numerator, you really messed it up, didn't you? Now it's x times the square root of x plus 1 plus 1. I'm not going to multiply those together. There's no reason to. Just leave it like that. But that denominator, hopefully you've made it somewhat better. What happens if you multiply the difference and the sum of the same two numbers together? What do you get as your result? Let's go back to A plus B times B plus A. I'm sorry. A plus B times A minus B. What does that give you? Say again? I don't know. It depends on the size. But in general, A plus B times A minus B. What do you get? I know A squared minus. No. If they're plus or minus, okay. A plus B times A minus B. Okay, let's FOIL it. A squared minus AB plus AB. You're squaring a binomial. When you multiply the conjugates together, and the last one is minus B squared, these two disappear. They add to 0, and you get A squared minus B squared. Y'all knew that. When you factored A squared minus B squared, you factored it to be A plus B times A minus B, don't you? Okay, you knew it, okay? So, what does that denominator become? These are your A's plus or minus B's. So the first thing squared is x plus 1. When you square a square root, you undo the square root, you get x plus 1. And then minus b squared minus 1. Hey, look at that. Plus 1 minus 1 in this case happens to go to 0. So now we have, shame, terrible. I did something wrong, didn't I? Yuck. Yeah, I don't like this. Okay. That'd be x times the square root x plus 1 over x. That's still going to an indeterminate form, isn't it? Or is it? Yeah, because x is going to 0. Boo hiss. I don't like this problem. Okay. Yuck. So this one, okay, this isn't the only way to do it. I thought I was going to skip some things. Nope, it turns out just as bad as before. Okay. Oh, no, it doesn't. What am I thinking? The x's go away. Why didn't someone catch me on that, huh? X divided by x is 1. Now we can plug in the limit of this as x approaches 0. And what do you get? 2. Exactly. So that limit should be 2. Okay, sorry about that. That's the whole reason I did it, to get rid of those. So that limit is 2. So if you want to, this is pretty easy to do, isn't it? With your calculator, let's start with 0.1. That's fairly close to 0, right? 0.1 divided by the square root of 1.1 minus 1. See what you get. We're going to do a shortcut of what they did before. X approaching 0, let's let it be 0.1. So 0.1 divided by the square root of 1.1 minus 1. Probably put those in parentheses. What do you get? Anyone? Got a calculator? Say it again. 0.1 divided by, open parentheses, the square root of 1.1, close parentheses, close the square root parentheses, minus 1, and close your other parentheses, equal. What do you get?
0.316.
Second?
0.316.
0.316. Goodness gracious, that's not very close, is it?
I may have done something wrong.
What's that?
I may have done something wrong.
Okay, let's step me through it again. 0.1 divided by, open parentheses, does yours have a square root key? Okay, square root, and it opens a parentheses, right? Okay, and then you're going to do 1.1, close that parentheses there, then subtract 1, and then close that parentheses and hit equal. You still get it? .06.
Is it 0.1 or 1.1?
Okay. What you're plugging in is x equal 0.1. 0.1. So 0.1 in the numerator. Divided by, open parentheses, then square root, which opens another parentheses, of 1.1, because you got 0.1 plus 1 is 1.1. And what you get?
2.04.
Is 2.04. Close to 2. And then you can do it on the other side and plug in a negative 0.1, and you'll get something else. Try that one. It's going to be very, very similar. Negative 0.1 divided by, open parentheses, square root of, now if this is a negative 0.1, add that to 1, you get 0.99. No, 0.9. Square root of 0.9, close that parentheses, minus 1, close that parentheses, equal what you get this time.
1.949.
Okay, 1.9. Again, very close to 2. Sure enough, both of them are close to 2. The closer you get to 0, the closer that number gets to 2. So the limit as x approaches 0 is 2, though you can't plug in an x equals 0. But this, the analytical way, gives us that 2. With a lot less calculated work. Okay? And they do the table in the book, and let's see, I think I probably need to erase all this. Oh, I didn't. So they start off with, they even came closer. The negative 0.01, much closer to that. They get 1.99499. Okay, that's pretty close to 2. Negative 0.001, even closer. 1.99950. Okay, negative 0.0001. 1.99995. That's getting close to 2 from the left. From the right, if you start at 0.01, plug that in, you get 2.0049, 0.001, 2.00050, 0.0001, 2.00005. So you see you are getting closer and closer to 2. Man, that's a lot of punching and buttons. If you did it analytically, you get your result right there. All right. Good deal. Any questions on that? Says an example, let's see, they may say this. All right. This limit is reinforced by the graph shown in this figure. Now, you're going, if you have a graphing calculator, I don't know what it does here, okay? I really don't know what it'll do there. You might get something that looks like this and looks like that. It may go bonkers there. And if it does, you have to control it, okay? But the thing is, remember when we did our rationalizing the denominator, multiply it by numerator and denominator, and we have the square root of x squared plus 1. Let's see what they would wind up with. Yeah, square root of x squared plus 1 plus 1. If you were to graph this, the x squared plus 1, that's going to shift it to the left 3, and then the plus 1 shifts it up 1. There would be that function. Except it's not defined there because here that would not be defined. Okay? But it approaches 2 from the left, it approaches 2 from the right. Stand up, sit down, fight. Okay, no, that was it. Make sense? No? I'm sorry? Oh, you're not getting it. Okay, let me walk you through it. I'm sorry. I meant to come back. Okay. Did you try to plug in here, or what we did before? Okay. And what did you, you don't have it written down. Let me write it down. When we did everything we did to it, that was f of x equal, wait, oh, no, you're plugging in numbers close to it. Is that right? Oh, okay. Let me watch you do that then. I'm sorry. I thought you were, okay. Let's see. Okay, do that. Okay, and you're doing into this, so that was negative 0.01. 0, 1, 0. Okay. Divided by, open parentheses. Okay. Square root. Okay. And that would be no, 0.99. Because it would be 1. I mean 0 here. I'm sorry. No. Negative 0.01 here. plus 1. Okay, which would be negative 0.01. Yeah, okay, now close that parentheses, and then minus 1. And then close that parentheses. Yeah, you get it, yeah. Okay. All those parentheses can really screw it up some. Okay, everybody got it? Okay. Now, they skip example 2, so let's us do example 2. Let's see if we can go back and, okay, let's do it here. Example 2. Find the limit of f of x as x approaches 2, where f of x is equal to, this is a piecewise defined function, okay? Good. Yeah, okay, I thought, okay. Where f of x is equal to 1 when x is not equal to, and f of x is equal to 0 when x is equal to 2. Okay? And what we want to do then is find the limit as x approaches 2 of this function here, of this f of x. Okay. Now, in a piecewise defined function like this, be very careful plugging in, okay? You might get something totally wrong, okay? In fact, here you do. Because if x approaches 2, we know the function is equal to 0. But is that the limit of the function? So let's let x approach 2, not equal to. Let's approach 2 from the left, okay? And all the way over from the left, f of x, when it's not equal to 2, that function's equal to 1, isn't it? That's what it says. 1 from the left, and it's 1 from the right. It's just a 2, it's 0, okay? So the limit as x approaches 2 is 1, but the actual value at x equal to is 0. So this one has a different limit from what the value is, okay? The others we were talking about had no value there. You couldn't plug in that. This one you can plug in x equal 2, but you would get a 0 if you plugged it in. But if you did the limit as you let x approach 2, anywhere other than 2 is equal to 1. Okay? So you'll see the graph. In fact, I'll draw it for you because not everybody has books yet. Here's what that one looks like. Okay? So f of x for all values of x except 2, at 2 it's equal to 0. For all other values, it's 1, 1, 1, except at 2 it's not 1, and then it's 1, 1, 1, 1, 1, 1, 1. That's the function. It's always f of x equal to 1 as long as x is not equal to 2. At 2 it's 0. Strange function. Whoever has functions like this, math books do. That's about all. But the limit as x approaches 2 from left or right is 1, but the value at x equal to is 0. Just a little weird thing. No wonder they didn't put it on the slide set. Okay? The limit does exist. Okay? Now we've talked about numerical approach and graphical approach. There's still to be, and I've shown you analytic approach, which I think is the best way to go. But now let's look at limits that fail to exist. And frankly, folks, they go through all sorts of mess here, stuff here. And this is one. Oh, okay, let's just hit. Let's show that this limit does not exist. Okay? Now, this is a little unusual one. This is an indeterminate form, because as x approaches 0, the absolute value of x would be 0, and x would be 0, okay? So, that's an indeterminate form. Not all indeterminate forms have limits. Some do, but some may not. This one doesn't. And here's why. How do we define the absolute value function? This is going way back in your memory banks. How do you find the absolute value function? Absolute value of x is equal to, it's a piecewise defined function. It's equal to x anytime x is greater than 0, or even equal to 0, right? But if x is negative, what is the value of it? Because absolute value is always positive, so you'd have to do a minus x, wouldn't you? Okay? Because if x is a negative number, absolute value is always positive, so you'd have to negate it, right? But if x is positive, you just write down the x. That's just absolute value, right? And by the way, this looks like that V-shaped function. Remember it? When you graph the absolute value function. Okay? Now, the question is, what's the limit of that ratio of the absolute value of x to x? Well, you do the same type thing here. Okay? The absolute value of x divided by x, this would be x over x when x is greater than, let's just leave it as greater than 0. I'm not going to put it in the equal to. Okay? And this would be minus x over x when x is less than 0. Right? Because the absolute value has these things. All you do is dividing by x, right? Now what is x over x? 1. So this is equal to 1 when x is greater than 0. What is it? This minus x over x. Negative 1. So this is negative 1 when x is less than 0. Of course, it's an indeterminate form at 0. So what's this one doing? Negative 1 coming this way, positive 1 coming that way. Guess what, folks? There ain't no limit. There's a left-hand limit of negative 1, a right-hand limit of positive 1, no limit at x equals 0. No way they'll ever have one. So this will indeed be one that does not exist. Because it's positive 1 coming from the right, negative 1 coming from the left, not going to happen. Okay? Does that make sense, sort of? Okay. Let me erase that and let's see if their description does a better job. Consider the graph of the function. Okay? And this is what I just was waving my arms about. And by the way, the YouTube videos doesn't pick up my waving arms. Okay? Doesn't pick up this. It only picks up what's I'm saying and what's projected on the board. So I'm glad this had this written here. Consider the graph of this. When you write the absolute value of x, it's just what we did. It's x when x is positive, negative x when x is negative. 0 is 0. Okay. But then when you do divide this by x and this by x, to give you absolute value of x over x, that goes to positive 1, that goes to minus 1. And now this is what the graph looks like. Negative 1 for negative x, positive 1 for positive x. No way that limit is ever going to exist. Now, they threw something in here we haven't talked about yet. We're getting ready to talk about it. And that's this little thing. Does anyone know what that is? Maybe from where you're sitting, it always looks like a minus 8 plus 8. It's not. There's the lowercase Greek symbol for the letter delta. Okay? There's minus 1, there's plus 1. That can't be minus 8 plus 8. That's a lowercase Greek letter delta. So minus delta to plus delta. Down here, for any minus delta, if delta is greater than 0, minus delta would be less than 0, you'd be this value. Up here, it's to be this value. In between here, it has no value. It can't ever bridge that gap. Okay? That limit does not exist as x approaches 0. because it's one thing to the left, a different thing from the right. And they throw it on the slide here. Here, well, yeah. I'm sorry, you see this, okay? I probably should have done that before we did the graph. Okay, that's exactly what that's showing. And here's where no, not yet. So no matter how close x gets to 0, there will be both a positive and negative values of x that yield either +1 from above or from the right-hand side, -1 from the left-hand side. Ain't never going to come to some limit, okay? And here's how you say that. Specifically, if delta, that's lowercase Greek letter delta, doesn't all look like a delta, does it? Is a positive number, then for x values satisfying the inequality that 0 is less than absolute value of x is less than delta. In other words, delta is a pretty small number, and anytime you're between 0 and that number, you can classify the values of x, absolute value of x over x, as -1 or +1 on the intervals, okay? And anything over here on this side is going to go to -1. Anything over here, no matter how small delta is, it's still going to be +1 here, -1 there, never, ever going to equal x equals 0, because they're not getting close, any closer, no matter how small you get. Sort of a weird way to say it, but we'll use that concept a little bit later. Okay? Because absolute value of x over x approaches a different number from the right of 0 than it approaches from the left side, limit does not exist. All right, so here are the three types of common types of behavior associated with non-existent of a limit. We've been talking about those who have. These are the ones that don't. So here's one. Alpha of x approaches a different number from the right side of C than it does from the left side of C. That's what we just saw. That will have no limit, always. Here's another one. Alpha of x either increases or decreases without bound as x approaches C. If that's happening, it has no limit. It's just getting bigger and bigger and bigger, either positive or negative. And here's the third one, a rather weird one. Alpha of x oscillates between two fixed values as x approaches C. So let's say it's doing this, and as it gets closer to C, it's doing it faster, but it's still oscillating back and forth. That's never going to converge. Elijah will converge, but not Castle. Okay. We may wind up getting, right now we're only missing one person, Kenesha. Okay. All right, so those are the three behaviors. If it's approaching different numbers from either side of C, not going to converge. It's not going to have a limit. If it goes either infinitely large or infinitely small, not going to have a limit. Or if it oscillates between two fixed values and never settles down as you get closer to C, that's not going to have a limit. Okay. Now, before we get to formal definition, they have a couple more examples. Okay, let's write them here. Example 4. Discuss the existence of the limit here. The limit as x approaches 0 of 1 over x squared. What do you reckon? Always the first thing I do, or just about always, is plug it in like Glade, you know. See what you can get out of it. What happens if you plug in a 0 here? Second? Not indeterminate. Indeterminate if you had 0 over 0. Undefined. If you have an undefined, this is going to be one of those that blows up. And sure enough, it will, because whatever x you put in here, you square it, you're going to get as x approaches 0, you're going to get an incredibly small, the closer you get to 0, very small but positive number. So as x approaches 0 from the left, it goes like this. As x approaches 0 from the right, it goes like this. Never is going to approach anything. If you have an undefined form, anything over 0 other than 0 over 0, not going to have a limit. Stop right there. Not going to have a limit. Okay? That's going to be one of those exploding points. Okay? So you can start plugging in values if you want to. They do in the book, but you'll see it doesn't happen. Now, let's do example 5. Now this one, and by the way, I think I mentioned this before, but let me say it again. This author has the best auxiliary information of any author I've ever seen. And every now and then you have an example, and they'll have a little red dotted line, it says, see larsoncalculus.com for an interactive version of this type of example. So that doesn't require any code or anything else. It's a website. You can go to it, and it's interactive. You can interact with them, okay, and see what's going on there, okay? So here is this problem, okay? Okay. Yuck. What? This thing does strange things sometimes. There we go. All right. Discuss the existence of the limit as x approaches 0 of sine of 1 over x. And calculus books love this example because it's wacko. I mean, that's not why they love it, but it is wacko. Okay? First thing I would note on it, not even messing with the sine function. This thing right here, what's it doing? Say again? And undefined. So when you see an undefined, you're not going to find anything, okay? It's not going to have a limit, okay? Because this thing, what is happening, as x gets closer to 0, right or left, this thing is getting bigger and bigger and bigger, okay? Now, what happens to the sine function, as you put in a bigger argument for it? What does the sine function do? It stays between plus and minus 1 forever. So no matter how big the number you put into it, sine is just going back and forth between plus and minus 1. If you put in a negative 0, something getting close to 0, that would be the negative number getting very, very large. If x is getting close to 0 from the negative side, like negative 0.1, then this would be negative 10. Negative 10 sine. And the sine is doing this. Okay? So no matter which way it's going, sine's staying between plus or minus 1. Always between plus or minus 1, never approaching any limit whatsoever. So this is that oscillating case. But why even mess with it? Take one look at it and say, undefined, leave it. It's not going to have a limit. It can't have a limit. But they call this the oscillating case. Okay. Now, they put in all fractions with pi in the denominator, which was a clever thing to do, but who would have thought of doing that anyway? If you just think through it, you know it's not going to happen. All right. Actually, then I should have done this slide. I got these out of order. All right. But before we go any further, bottom of the page here, in addition to that one we just did, you go back and find that one. In addition to f of x equals sine of 1 over x, there are many other interesting functions, so they say, that have unusual limit behavior. An often cited one is the, I don't know how to pronounce his name. If that were French, I would say Dirichlet, because the ET is usually a long A sound. But he's a German, so it may be Dirichlet or something like that. I don't know how the Germans pronounce it. But here is his function. What a clever little function. I see almost no use whatsoever for it, but he's famous for it. Here's what it is. F of x is equal to 0. It's another piecewise defined function if x is rational. Okay? It's 1 if x is irrational. Now, do y'all remember what the difference in rational and irrational numbers are? No? Okay. Rational. There's the word rational. What if I cover up the last 3 letters? What do you have? Ratio. What does ratio mean? A fraction. Division of 2 integers. As long as that bottom one is not 0. Exactly. So any number that can be expressed as a ratio of 2 integers, as long as the denominator is not 0, that's a rational number. So any fraction, how about decimals? Decimal forms of a rational number are always either going to terminate, they go so far and stop, or they go so far and start repeating some unit. Like 0.735, 25, 25, 25, 25. That's a rational number. Okay? So therefore, an irrational number cannot be expressed as a ratio of 2 integers. Is one definition. And the other is decimal form. We go infinitely with it never terminating and never repeating a pattern at all, no matter how far you go. So, what a weird function is it? Can anyone come up with an irrational number for me? Name an irrational number. Pi is. Pi is one of the most famous. There's another one called E. Okay? And there's lots of others that you probably have dealt with before. Square root of 2, square root of 3, square root of 5, square root of 6, square root of 7, square root of 8, square root of 10, square root of 11. It's cube root of 1, cube root of 2, cube root of 3, cube root of 4. There's a ton of irrational numbers. Your radicals, unless you happen to have a perfect square, a perfect cube, or something in there, those are going to be irrational numbers. Okay? So this is one weird formula. Starting with 0, that's a rational number. So alpha 0 would be 0. And then anything to the right of that, you have an infinite number of rational numbers to the right. You have an infinite number of irrational numbers to the right. So you would have a bunch of zeros here for the rational numbers and a bunch of ones here for the irrational numbers. And you can't tell where the holes are because they're so close together. Okay? So it's a really weird function. Okay? He must be strange. Okay. But anyway, if you like strange people, you can write, who in the world was Dirichlet? Whatever his name is. Or, how did he come up with this function? Or maybe even better, what is that function used for? It may actually have a real use. Maybe in your field of study. I don't know. I doubt it, but you could check. So, now, I want to warn you on a couple things. If you do choose to write on Dirichlet, this is not your source. The idea came from here. You have to get your source somewhere else. And this book, he goes even more. That's good old clarsoncalculus.com to read more of the biography. That can't be your source either, okay? You have to go somewhere outside the book and it's other resources to get it. So don't be using this. You can get the idea from here, but you get your resources somewhere else. Okay. Now, they also mentioned something else here, a technical pitfall If you're trying to use your graphing calculators to see if these things have limits, these ones that oscillate like this, you're probably going to get some really weird results, but it may look like you actually have a limit. Because those graphing calculators, if you haven't noticed, they do some delta x. They don't do every value, they just do some incremental value. And the smaller the increments are, it may do this. And some of these, the more they're moving, then the more they try to connect the dots, and they don't always connect very well. So don't let your calculators make you think it does have an answer when it really doesn't. Okay? They show this one. Okay, I won't get into that. Let's move on to the formal definition of a limit. I usually don't like formal things too much. The shoes hurt. The clothes are uncomfortable. Never mind. Okay, let's take another look at the informal definition of a limit. If x becomes arbitrarily close. Now that's what I call a weasel word. What does arbitrarily close mean? Somehow close to it, but how close? We don't know. To a single number L, f of x is approaching that L, as x approaches C from either side, then the limit of f of x as x approaches C is L. And that's how we write it. Okay? Now that's the informal definition. At first glance, that definition looks fairly technical until you start noticing what is arbitrarily close. Okay? That's not very technical. Even so, it's informal because of the exact meanings have not been given to the two phrases as it becomes arbitrarily close. So what does that mean? Or as x approaches C. Well, what does it mean to approach C? How close does it have to be to C? Those are weasel words. They're imprecise. That's why it's informal definition. So the first person to assign mathematically rigorous meanings to those phrases was not Isaac Newton, nor Jeffrey, whatever his name was, Leibniz. This guy came much later, Augustin Louis, I think you pronounce it Cauchy, French, I believe it was. And his epsilon delta, remember that good old delta? The epsilon delta definition is the standard used today. Okay? Now, in this figure, the epsilon, that's this little symbol here. I'm trying to think that's the lowercase, lowercase e in the Greek alphabet is called epsilon, and that's how it looks. Okay? Sort of looks like an E too, a little bit, kind of. Okay? And the lowercase delta we already ran into. What epsilon is how close you want to be to that limit L. There's some small positive number, and if L plus E is going to be above it, L minus E is going to be below it. I say E, but it's actually epsilon. Delta is how close you are to the input value. This is the output value, the L, the f of x. This is the input value down here, your C. Okay? And you get a delta close to C. And delta, again, is a small positive number. So C plus delta is going to be just past C. C minus delta is just going to be here. So basically what we say, the phrase as x becomes arbitrarily close to L means that x lies in between L plus epsilon and L minus epsilon. That means arbitrarily close. For any size epsilon you happen to choose, then you can find the delta small enough to make sure that when you plug it in here, it's always going to be between plus or minus epsilon. That's what it means. Now we're not using arbitrarily close or fairly close or approaching. You're actually setting a value. For any given epsilon, can you find the delta that guarantees you're between that? That's basically what your formal definition is going to be for you. So let's see what that formal definition is. Now, they use these absolute values because remember we said epsilon being a small positive number. So whether f of x or L is bigger or smaller, it doesn't matter. The absolute value of the difference is less than epsilon. Okay? Well, if f of x is greater than L, then that'd be f of x minus L. But if L was actually greater than f of x, then you have to do the absolute value have it less than. So similarly, the phrase as x approaches c means there exists a positive number, small positive number delta, such that if x lies on either side of the interval, c minus delta to c or c to c plus delta, anywhere in between c plus delta and c minus delta, if your input is that, then you're arbitrarily close as x is approaching c. This fact can be concisely expressed by the double inequality. 0 is less than the absolute value of x minus c. That's always going to be some positive number. That's why you don't have to have a negative here. So that's less than delta, which is always a small positive number. Okay. That's your definitions. So here's what we got. The first inequality, that x is less than or equal to 0 is less than or equal to the absolute value of x minus c. Okay? That means that x is not equal to c. Because if it was equal to c, that'd be equal to 0. So if x is anything close to c but not c, then the absolute value of that difference is going to be greater than 0. Okay? The distance between x and c is more than 0. That just says x can't equal c. Okay? Not necessarily. The second inequality on the other side says that the difference is less than that, whatever that limit is, that small value you have. The x is within delta units of c. Okay. It's within a distance of delta from c. Okay. So here's the formal definition. What you've been waiting for all your life, right? Let f be a function defined on some open interval containing c. Okay? So the function f is defined around this value c. Now f may have some discontinuities in it. If it does, they're not near c. So it's a function defined on an open interval containing c, except possibly at c. There may be a discontinuity at c. That's okay. But everywhere else around c, the function is defined. Okay? Basically, that says there is a delta around c, so that the function is defined there, as long as the function is equal to c. Now, this statement here, the limit as x approaches c within that interval, open interval, from the left or from the right, the f of x, that function, within that, except necessarily at c, it may not equal it at c, but within that, it's approaching, the function is approaching L. Now, so how do they go about saying that? That means that if you choose an epsilon greater than 0, some positive number epsilon, small as you want to go, as small as you choose to do it, then you can find the delta. There exists some delta greater than 0 also, such that if x minus c, absolute value of x minus c is between 0 and delta, then you're guaranteed that the absolute value of the function minus L is less than epsilon. If you get close enough here, you're going to be close enough here. Close enough on the x-axis to make it happen on the y-axis. That's your formal definition. So, we're going to start with one that's incredibly simple. Okay? Do y'all buy this? That the limit of 2x minus 5 as x approaches 3. What would that be? You tell me. Okay, yeah, you plug in x equals 3. 2 times 3 is 6. Minus 5 is 1. Yeah, that limit's 1. You know it is. Guaranteed. Okay? Does it fit this? Find the delta such that here's your function, there's your limit. The difference of the function and the limit is less than 0. Less than 0.01. You chose a delta, chose an epsilon greater than 0 of 0.01. Okay? Now, And you want this to be true anytime 0 is less than x minus 3 is less than delta. If you're close enough there, you guarantee this is going to work. Okay? Now, this one's pretty simple to do. I wish they all were this simple. Sorry, they won't be. Let's clear the parentheses here. That would be 2x minus 5 minus 1, right? Those parentheses are doing nothing but showing that's the function, that's the limit. Okay? The absolute value is less than 0.01. Okay? Well, let's combine like terms. That would be 2x minus 6 less than absolute value. Oops, I already put the absolute value, sorry. Okay? Less than 0.01. Okay? So we're looking for a delta that's going to make that true. Well, guess what? I can factor out a 2 from there, can't I? 2 times x minus 3 less than 0.01. Ho, that's looking close, isn't it? All we have to do is now divide by 2, and you got absolute value of x minus 3 is less than 0.005. There's a delta greater than 0 that will make that true. And this certainly is less than 0. I mean, greater than 0. Okay? So we found the delta. It's all you have to do. If you can find the delta, it's guaranteed to work. You found that the limit exists. And we knew that limit existed because you plug it in, it's there. Okay? And this shows you, sure enough, that's it. There's the delta. You have 0.005. Guarantee you'll be between 0.01 up here. Okay? You have to get it pretty tight, but you can do it. If you can do that, you prove the limit exists. Okay? Now, y'all want to hear the good news? As soon as we're through with these sections here, you don't ever really have to do these much anymore. It's just telling you what these things are. Okay? And then we'll get into real calculus. I'm sorry, I shouldn't say that. Okay. All right. That was example 6. Okay? Let's watch how they did it. They probably describe it better than I did, so let's do that. Okay? In this problem, you're working with a given value of epsilon, named epsilon equal to 0.01. I didn't write it down, but I probably should have. You're looking for a delta that will make that true. And that's what you proceed to do then. You write this, which is exactly what they tell you. You would try to do a connection between this and that. And if you just start doing the math that's in here, which is what we did, that would be absolute value of 2x minus 6. That's 2 times the absolute value of x minus 3. And that's less than 0.01. Then divide by the 2. And you got absolute value of x minus 3, which is what your delta needs to be less than. That's it. Now, does it sort of feel like you're going around your elbow to get to your ear? Yeah, it does. I remember the same feeling. But frankly, once you get these knocked, then you don't have to worry with them much anymore. Okay? I shouldn't say it like that, but boy, that's tedious. Okay. The choice works because if you choose a delta 0.005, you're guaranteed to make that 0.01. That's 1.01. So that limit does exist. Koshi, if you were still alive, no, I wouldn't say that. Okay. So as you can see in this example, and here was the example they gave earlier, 2x, what was that? 2x minus 5. Y-intercept is down here at minus 5 somewhere, and the slope is a 2 going up, 2 for every 1 it goes over. So Yeah, here it is, 2x minus 5. Y-intercept is negative 5, and the slope, if you go from, say, 2 to 3, you're going from negative 1 to plus 1. That's just rise of 2 for every run of 1. So there's your slope. And because of that, if your epsilon up here was 0.01, your delta here had to be, because you're going up 2 to 1, half of that. Okay, 0.005. That works in a linear problem. When they're not linear, they get a lot more complicated. But there you have it. You're guaranteed to be within that. And they actually plugged in the value. If the delta was 0.005, 0.005 less than 3 would be 2.995. Plug that in, you get that value there, which is within 0.01. And if you plug in 3.005, you get this one up here, which is within 0.01. If you plug in the 3, you get exactly 1. That's all you have to do. In the real life, plug it in. If it works, you're done. You're done. Okay? Plug in x equals 3, you find your limit at 1. Okay? This shows that it's indeed true. Whoa! Okay, that was example 6. They're skipping examples 7 and 8, so let's do those fairly quickly. All right, let's do them here. Oh boy, they showed you the easy one, and they skipped the harder ones. Okay. Use the epsilon delta definition of a limit to prove that, oh, this one's not bad. The limit as x approaches 2 of 3x minus 2. You tell me what you think that limit is. 4. You're absolutely right. So why go through this? Well, they told us to. Okay? Now, when I talked about my calculus professor, boy, he had this stuff down pat. He started this litany, and we all got into the rhythm of it. Had no clue what I was talking about, but he said, let epsilon be greater than 0. Okay? Okay. Then there exists a delta greater than 0 such that, okay, I'll put a comma there, such that for every, I can't remember how he said it, but anyway, you write down this part. It's the function minus the limit. Absolute value of 3x minus 2 minus 4. That has to be less than epsilon if there's a delta 0 less than, and here you go here, absolute value of x minus 2 less than delta. That's what we're trying to get. That there is an epsilon, no, for a given epsilon greater than 0, this difference, this will be less than that anytime your x minus 2 is less than delta. There's got to be a delta to do that. Okay? Well, I did it before, you do it this time. What would you do first? Okay? Clear parentheses and combine like terms. What do you get? 3x minus 6 less than epsilon. Okay. Now, did they give us an epsilon here? No. Okay. Keep going. What can you do next? Factor out a 3, and that leaves you x minus 6. X minus 2, sorry. Okay. Yes. Wait just a second. Then divide by 3, and you get absolute value of x minus 2 less than epsilon over 3. That's less greater than 0. There you have it. What's the delta going to be? A third of what the epsilon was. Give me an epsilon. As small as you want it to be. 1/1,000,000th? Is that small enough for you? That's really small. Can you get a delta that's going to guarantee your value will come within 1/1,000,000th of that? Yeah, just divide 1/1,000,000th by 3, and that gives you, let's do 3/1,000,000ths. Okay, 3/1,000,000ths here, then 3/1,000,000ths up here, that make it 1/1,000,000th down there. Okay, guaranteed. No matter how small your epsilon you choose, you can come up with a delta that's going to guarantee you within that. These are the easy ones that come out that neat. Unfortunately, life is not so easy, okay, most of the time, okay? So, let's do example 8. And this is one that's not so straightforward. Use the epsilon definition to prove that the limit as x approaches 2 of the function x squared. You tell me what you think that limit would be. 4. Pretty easy, huh? Okay. Now, using epsilon delta, we want, for any epsilon greater than 0, let epsilon be, there exists a delta greater than 0. My writing gets worse the more I go here. Okay, such that for any absolute value of x squared minus 4, that's the function minus this, less than epsilon, okay, then absolute value of x minus 2 is less than delta. Okay, that's what you're trying to get to. Okay. Not going to be nearly as pretty as the others are. Okay? Now, you're trying to get something here to look like something here. Anyone want to think of something you might be able to do here? Yeah, let's factor it. And what does that give us? Absolute value of x plus 2 times x minus 2 less than epsilon, and that would imply that 0 less than absolute value of x minus 2 less than delta. We're trying to find a delta that's going to make that true. Okay. Now, here's where things get a little strange. To get that delta, that's what we're looking for. Values of x close to 2. Okay? There's those weasel words again. How close do you need to be? So if you choose x in the interval from 1 to 3, okay, 1 to 3, that's going to be within 1 of 2, right? Okay. So let's start with that, okay? If that's within 1, and that's what we're going to say, for all x's in that, then this part right here, if your x is within 1 of 2, this is going to be 1 plus 2 would be 3, and 1, how do you say that? Well, 1 to 3, okay. If x, you're within that, so if you're, let me make sure I say the words right. So x plus 2. All right. Let's first assume x is in the interval of 1 to 3. Okay? Now, if x is 1, this one right here would be 3. If x is 3, this would be 5. So which is the greater of those two numbers? 5. Okay. So we'll start with that. Okay? So if x plus 2 is always less than or equal to 5, okay? In other words, you're no more than 1 away. The delta is going to be smaller than 1, okay? Then that's going to be 5, okay? So if that's the case, if that's the biggest this can be, then that would be 5 times x minus 2 less than epsilon, divide both sides by 5, and your delta would be epsilon over 5. Okay? So, if the delta was 1, then if the delta was 1, the epsilon would be 5. Okay? So if you choose an epsilon as large as 5, it's not very close to 2, by the way, then your delta only has to be 1. All right, that takes care of the big case. Now we can go to the smaller case. Okay? If that's the biggest it can be, then this is what the first part of that is. If that's the biggest it can be, anything smaller than that is easily going to fall within that. So if your delta is anything, if your epsilon is anything less than 5, okay, then take a delta of epsilon over 5, and it always is going to guarantee it's going to be within that. And again, this is really Weasley, that's why I generally don't like having to do these. And guess what? You can get complex looking things and they get even worse. You have to just figure out some way to get this into a form like this, and then pick something arbitrary here that you can deal with it. Anything less than that, you're going to be fine. Then you deal with this, and sure enough, you get there. It's really slippery. But the fortunate thing is we don't have to do it often. So let's just get it over with. Okay. Let's go quickly and look at the concept checks here. Oh, there's nothing really you have to do there. It just is reviewing what we've done. First time I taught from this book, so I'm trying to make sure I'm covering everything. Now, homework exercises here. Do any of the odds 5 through 9. Okay? Now, I want to point out a couple things to you. I think I've mentioned this before. All the odd number answers are in the back. Okay? So try to do 5 through 9. If you can't get the answer in the back and you can't figure out how to get the answer in the back, then you can go to calctrack.com and see tutorial help and worked out solutions. Okay? Now, if even looking at that and following that, and you still, I don't know why they did this, then do number 5. And you notice number 5 is a red letter, right? And that red letter also has this thing on it, this symbol here. We used to use barcodes, then we went to two-dimensional barcodes is what I call this. If your phone will read this, that will take you directly to the calcview.com. And number 5 is worked out there in gory detail. So you can either go to calcview.com or get your phone to read this, and it'll take you straight there, and then you can see number 5 worked out. Okay? So, that's 5. They don't do all of them that way, but all the answers are in the back, and on calcchat.com, only the red ones are on CalcView. Then do any of the odds 11 through 17. And that's sort of unfair because It jumped into something, well, no, you can still do it. 11 through 17. Then do number 19, that's the only one like that. And then do any of the odds 21 to 27. Again, all the odds are always in calcchat.com. 23, that symbol there will get you to calcview.com for 23. Then do 29, and it's there at calcview.com. Then do 31, it's at calcview.com. Then do 33, it's only at calcchat.com. And then do any of the odds 35 through, well, 37, 35 or 37 or both, okay? Then do any of the odds 39 to 43, 41's at CalcView, all those are at CalcChat. Any of the odds 45 to 55, and 47's at CalcView, all of them are at CalcChat. Try to do 57, okay? Don't get too bogged down with the upper level if you don't want to. 59 is just a writing exercise. I don't want to expect you to write it, but sort of think through it, okay? 61 is thinking of modeling. You don't have to do much there, but not a bad idea to try to think through. Exploring concepts, 63 or 65. You may find those interesting, but don't get too bogged down with them. 67 is actually a practical type of problem, so you might want to look at it. 69 is an estimating. We haven't done that, but you can sort of take a look and see if you can figure it out. 71 is a graphical one that requires you to use a graphing calculator. If you don't have one, don't sweat it. And then there's some true-false, 73 and 75. I don't really like true-false questions in math because there's so many little things you could twist and make it completely wrong or the opposite of what you're expecting. But look at these graphs, think through these, see if you can do it. You won't see a true-false on a test, but 77, you can think through that one. 79, you can think through that one. Again, it's using a graphing calculator. And then if you're into doing proofs, and some of you may really be gluttons for fun, masochists, something, you can do either 81 or 83 if you would like. And then 85 is what they call the Putnam Exam Challenge. I remember reading this somewhere, evidently some Putnam Prize that they have. If you're really into something like that, you can look at 85. I wouldn't waste spend a lot of time on it, okay? Up to you. We'll pick up with 1.3 next time. Have a good weekend. So we're missing Tanisha today.